How's it going? Hope everyone's doing alright. Do you all have any questions before we get started with the review? Yes, it's the very last part of the last question. When we go over the review today, I will present to you with a different question that will be like the one on the actual exam. Mm-hmm. Okay. So, looking at the review, let's see. Test 2 review. Please let me know if there's anything clarified, anything that you need clarified along the way, and if there's something I missed or didn't explain properly, or you're just not sure about. Let me know. All right. So problem 1. We have a small bag of jelly beans. We have 40 red jelly beans. We have 33 blue jelly beans and 27 purple. Which, if we add those together, that means we have 100 total. Okay, so question A, 1A, was the probability that we pick 2 jelly beans without replacement and we select 2 that are purple. Well, this is a conditional probability, but we don't use the formula. We just use it from a logic standpoint. And the idea is that we look at, okay, what's the probability of picking a purple jelly bean on the first try? Well, we know of the 100 total jelly beans, 27 of them are purple, so we have a 27 over 100 probability of choosing a purple jelly bean on the first try. Now, on the second try, if we've taken the first one out, that means there's only 99 jelly beans left, and because we already chose 1 purple, there's only 26 purple jelly beans left. So on the second purple jelly bean, there's only 26 remaining of the 99. Now, the rule says that if we want both of these events to happen consecutively, to find the probability, we multiply them together. Okay, so we multiply 27 times 26, which is 703. And then 100 times 99, which is 9900. And we divide those together. Here we go. And for that, we get 0.071. Now, most of the test is going to be fill in the blank, and what's going to happen is when you submit your test, it's going to be graded automatically by the quiz software. Okay, and it's going to go through and check, did you put 0.071 in the blank? So we cannot put any extra spaces there. If you put a 0 in the front, that's actually fine. It'll accept that. But we cannot put extra spaces. You can't put 703 over 9900 equals 0.071. It's not going to know the difference between that and the actual answer. So make sure you round properly to 3 decimal places, as will be given in the instructions. And we don't put any extra spaces in here or equal signs or anything like that. That way the auto grade feature will actually grade it correctly and you'll get your points. Now I'm still going to go back through and check to see if there were any mistakes in the grading, because I've seen that in my other classes on other tests already, and I don't want you all to lose those points. So I'll make sure that that doesn't happen, but preferably would not happen in the first place. There's really only one problem, I believe, that I'll have to go in and grade, and that's on the expected value problem, just for your explanation of that. So something to keep in mind, but I'll put that in the instructions on the exam already, so it's already there. Okay. The second probability we wanted was the first is purple and the second is red. Okay. So we have our first jelly bean and our second jelly bean. Now the first one being purple, we know, again, 27 of the 100 jelly beans are purple. And for the second one being red, we know that there are 40 red jelly beans. Even after we've taken out one purple, there's still 40 red jelly beans of the 99 remaining jelly beans. So 40 over 99. So we know that there's now one less jelly bean, but all the red ones are still there. We took out one purple, the 40 reds are still intact. So 27 over 100 times 40 over 99. You know, it's still 9,900 on the bottom. 27 times 40, that's 1,080, I believe. Yeah, we'll go with that. And so 1,080 divided by 9,900. So we get 0.109. Okay. So that'll be our probabilities on each of those two events, using the multiplication rule, it turns out. Okay. And so we move on to problem 2. For problem 2, suppose you bought a digital album from your favorite artist and set iTunes to play the album in random order with no repeats. So again, that's without replacement. So it's actually a very similar problem to the jelly beans, although it's stated differently at the outset. So the album has 11 songs, of which we like 7. Now, what that means, if we want to break it down into the terms of problem 1, what it really means is that we have 7 that we like, there's 4 that we don't like or dislike, and then we have 11 songs total. Okay? So event A, part A, what is the probability that we like both songs that are played first? And so our strategy is just like where we chose 2 purple jelly beans. We look at the probability that we like the first song, and then the probability that we like the second song, and then we'll multiply them together. So for the first one, we know there's 7 songs that we like out of the 11 songs total, and so there's a 7 out of 11 chance that we like the first song. And for the second song, let me move this up here. There we go. For the second song, we know there's of the 7 that we like, we already played 1, so there's still 6 more that we like. Right, so it'd be 6 out of 10. So now by playing the first song, we know there's only 10 songs left to play, and of those 10, 6 of them we like. Multiplying across, 7 times 6, 42. 11 times 10, 110. And then we'll just divide those together. And again, we round to 3 decimal places. So make it 0.382. So not a bad probability that we'll like both of the first 2 songs that we play. Alright. Now part B. We want the probability that we like neither song. That means we dislike the first one and we dislike the second one. Now, of the 11 songs in the playlist, we dislike 4 of them, so there's a 4 out of 11 chance that we dislike the first song. We'll press skip and move on to the next one. But after we play the first one, that means there's 3 songs left that we dislike of the remaining 10 songs in the playlist. So 3 out of 10 chance we dislike the second one. Okay. Same situation, but this time we're drawing from the pool of songs that we dislike instead of the ones that we like. And we multiply these together again, so that will be 12 out of 110. And so dividing those, we get 0.109. Good. Excuse me. Now part C, we want the probability that we'd like at least one of the two songs that are played. There's really two ways to do that. One's a little bit easier than the other. We could look at the probability that we'd like the first song but not the second. We could look at the probability that we'd like the second song but not the first. And we could like the probability, or look at the probability that we'd like both songs, and then add all three of those values together, and that'll give us the probability that we'd like at least one song. And that's fine, but it's three different calculations. Now, the easier way, or the way that I would prefer for you to do this problem, is to use the complementary probability. Complementary probability, the way it works is if we want the probability of at least one, then we know the we'd take 1 minus the probability of its complement. What is the complement of at least one song playing that we liked? It's not 7 out of 11. I'm thinking more generally. When we say that we like at least one song, what's the opposite of liking at least one song? Either we like at least one song or blank. Well, we're going to play two songs. Okay? 1 or 2. So either we like at least one of them, and when we say at least we like at least one, it could be either the first one or the second one or both. But the other possibility is that we dislike both of the songs. Okay? And I mentioned this when we went over complementary probability. The foundation that we use here for our applications of complementary probability is that the probability of at least one thing occurring is 1 minus the probability that none of those things occur. Okay? So if we want the probability that we like at least one song, then it's 1 minus the probability that we like neither of the songs. Okay. Now the probability that we like neither of the two songs that are played, we've already calculated that. That's this number right here. Part B, we're finding the probability that we like neither song. And so we've already found this probability, so we'll just fill in the value, 0.109. From here to there. Okay. And so we subtract that from 1, and we get 0.891. And that will be the probability that we like at least one song. Okay. That one's a little bit tricky, I'm not going to lie. But you'll have a very similar question on the exam, where in part B, we want the probability that we like neither thing, and then part C, we like at least one thing. So we actually do it the same way, just take this answer and subtract it from 1 to get our answer here. Okay. Okay. That takes care of problem 2. Alright, problem 3. We start off with a table. And this is the different appliances and the different colors or finishes of these appliances that are available at a certain department store. So let me draw this table. Let's see, we have 4 rows and 5 columns. Okay. So we have refrigerators, dishwashers, these are available in stainless steel, black, and white. And we also include rows and columns for total. And then just filling in the numbers, we have 13, 11, 24, 9, 12, 21, 3, 2, and 5, and 25, 25, and 50. Okay, so we have 50 total appliances available. At least these two types, refrigerators and dishwashers. And we have the number of each type for each color, or finish, whatever we want to call it, for each. So we know we have 24 with the stainless finish, 21 black, and 5 white, 25 refrigerators, 25 dishwashers, and 50 appliances total. Now we have 5 questions based on this table. So A, what is the probability that an appliance selected at random is a dishwasher? Well, if we want the probability that we randomly select a dishwasher, that would be the number of dishwashers out of the total number of appliances. And so we know there's 25 dishwashers out of 50 total appliances. 25 out of 50. And we make that 0.5. Even though I've said enter 3 decimal places, if we put 0.5, it'll still count as correct. Okay. Second question B. We want the probability of selecting an appliance at random and picking one that has a stainless steel finish. And that would be 24 out of 50. Good. So 0.48. Now, C, D, and E both incorporate multiple scenarios, but we have to pay attention to which type it is. For C, when the probability an appliance selected is both white and a dishwasher. Yeah, so it has to meet both requirements. So we look at our white colored appliances and our dishwasher appliances, and there's 2 of those. 2 of those that meet both requirements, and that's 2 out of 50. 0.04. Okay, D. We want either a stainless steel appliance or a refrigerator. Now, when we have an OR statement, we want to make sure that we use the addition rule. So our addition rule, let me write this down. So it's the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both A and B. Okay. Now in this case, A would be like our stainless steel appliance and B would be like a refrigerator. So we want the A, probability of stainless steel, plus the probability of B, that's the refrigerator, and minus the probability of both. Okay. Now for the stainless appliance, we already know that's 24 out of 50. For the refrigerators, we know that makes up 25 out of 50 appliances. And what about both? How many appliances are both stainless steel and they are a refrigerator? That would be 13 out of 50. Okay. And so we'll just combine these together, 24 plus 25, and then minus 13. So it's 49 minus 13 is 36 out of 50, which comes out to be 0.72. And I don't know if I have room for E, but we'll try. What is the probability that an appliance selected at random is black, given that it's a dishwasher? Okay. Now, let me actually use a space up here. Okay. Now the rule for this is conditional probability. Probability of B given A is equal to the probability of A and B divided by the probability of A. Okay, so first of all, given, that's what our vertical line means here. But we want to find the probability of both, that it's a dishwasher or a black colored dishwasher. Divided by the probability that we select option A, which is the whatever's given. In this case, it's given that the appliance is already known to be a dishwasher. So how many appliances meet both requirements that it's a dishwasher that is black? Yeah, it's black dishwashers. So it's 12 out of 50. And then the probability of even choosing a dishwasher in the first place, we already calculated that once. That was 25 out of 50. Right here. Now, what happens here is because both of these are divided by 50, the 50s cancel. So we get 12 out of 25. And so 12 out of 25, if we calculate that, is, I believe that's 0.48. Yeah. Okay. That one's probably the trickiest of the bunch, but also don't let the OR statement fool you. You have to use the addition rule there in order to get the correct result. Okay. Moving on to problem 4. So we're selecting numbers at random from a hat, 1 through 10. And we have 3 different events that are defined. Okay. So event A is even numbers, which is 2, 4, 6, 8, and 10. Event B is power of 3. Which is 1, 3, and 9. And event C is simply less than 4. Which is 1, 2, and 3. What do you mean, what happened? Did it cut off? Okay. Daviana, you might try to refresh. Good, good. I won't have to type it out then. Yeah, this actually happened during my review on my Tuesday-Thursday class last Thursday. It actually did get cut off for everyone, and ended up having 3 parts to represent the entire review. So if you want to watch the review, there's like 3 different videos from my other class. So I'm really hoping we get all one concise video here, because that's much easier, I think. So anyway, I did link them, so it wasn't a big deal, but it's kind of annoying, you know. When you go to YouTube, you don't want to watch a video that's in 5 parts. Just watch the whole thing, you know. Anyway. What is our probability of A? Well, for event A, we know there's 10 possibilities total as far as what number we could draw. But how likely, and I did a terrible job writing these numbers, and I apologize for that. How likely are we to choose one of those numbers? Five out of 10. And again, make sure you enter your answers as decimals. That's how the computer's going to be set up to recognize those for the purpose of grading. So we know this. We know it's 5 out of 10. But we'll go ahead and divide that and make it a 0.5. So that's A. What about the probability of B? B is 3 out of 10, or 0.3. There are 3 numbers here, even though it doesn't look like it. And then the probability of option C, that a number we draw is less than 4. Is that 4 numbers? Three, yeah. Usually I go with all 3 events having different numbers of outcomes. This one has the same number of outcomes for both B and C. That's okay. Probably my writing was throwing you off too. I apologize for that. I look at this 3 and it's almost like my brace. So anyway, it certainly is causing me some distress. Anyway, part D, continuing. We want the probability of B and C. Now when we find the probability of B and C, the intersection of those two events, we have to look and see how many outcomes do they share in common out of the 10 total. How many would that be? Zero? There's more than zero. Two? Make sure you're looking at B and C, Davion. Yeah, 1 and 3 are both in common. So that's two numbers that they share out of 10, or 0.2 probability of that occurring. Okay. Now, event E, or sorry, problem E, we want the probability that B or C is successful. And again, anytime we see or, we have to use the addition rule. That says this is the probability of B plus the probability of C minus the probability of B and C. Okay. Now, all three of these things we've already found. We found the probability of B is 0.3, probability of C, 0.3, and we found the probability of B and C, which is 0.2. So for this problem, the way I've set it up is we just find the numbers we already found and plug them in and simplify. And so that'll be 3 and 3 is 6, minus 2 is 4, so 0.4. Okay, part F, we want the probability of B given C. Now, when we find our conditional probability like this, on top we have the probability of B and C, just the two of them together. So the intersection of those two events. On the bottom, we put whichever one comes second. Okay, so we're given that event C has already been determined to be successful, so we'll divide by probability of C. This place is where I've seen the most students get mixed up or make a mistake, is they put the wrong letter down here. Okay, so we have to be very careful of that. You will have the formula, but the formula will have A's and B's in it rather than B or C, so we have to make sure if it's different, we have to adapt it to the pair of events that we have in the correct order. And that's what's a little bit confusing sometimes. Now in this problem, again, all these values we've already found, so we just have to plug them in. Probability of B and C, we saw that was 0.2. Probability of C, we already calculated that as 0.3. And so dividing those, we get 0.667. Okay. Now in G, we again have a have an or statement, so we use the addition rule. Okay. In this case, we've already found both A and C, or probability of A and probability of C, sorry. Probability of A is 0.5, and probability of C is 0.3. What about A and C together? So if we look at events A and C, are there any outcomes that they share in common? Yes, they have one number in common, specifically the 2. So they have the 2 appearing in both lists, so that's the only one that's in common between them. So it's 1 out of 10 or 0.1. Is everyone okay with that? Okay. And then we just combine 0.5 plus 0.3 is 0.8 minus 0.1 is 0.7. Alright, last we have H, which is probability of A and B. Now again, this is just the intersection of those two events, so A and B. Do A and B have any numbers in common? 2, 4, 6, 8, 10, 1, 3, 9. No, they do not. So with 0 numbers in common, our probability of that occurring is 0. Okay. That takes care of number 4. Alright, now number 5. A game is suggested to you at a party. A person has numbers 1 through 10 in a hat. You'll pay them $1 to play. If you draw 1, 2, 3, or 4, you will pay them an additional $1. If you draw 5 or 6, you win $1. 7, 8, or 9, you win $2. And if you draw the 10, you'll get $3. So 1, 2, 3, 4, we pay $1. 5 or 6 wins us $1. Well, 7, 8, or 9 wins us $2. And the 10 will win us $3. Okay, so that's our kind of a summary of what was said there. And the way I have this set up on the actual exam is what I've done is we have 4 columns like we did in class. We have outcomes, we have net winnings, which is x, we have p of x, and we have x times p of x. Okay. What I've already done on the exam is I've filled in this first column because that just groups the different outcomes together as far as having the same results. And what I've done is I've made blanks in each of these 4 spaces for all 3 columns. So there's 12 blanks here. And as you may guess, each one is worth 1 point. Okay, so the question is, we paid $1 to play, and if we drew a 1, 2, 3, or 4, we paid an additional $1. So where do we stand if we happen to draw the 1, 2, 3, or 4? What if we? What is the net change to the money that we have in that situation? -1, -2. We paid $1, and then if we draw one of these 4 numbers, we pay another $1. That means we've paid $2 with no winnings to show for it. Okay. Now, again, we start off, we pay $1. But if we draw a 5 or a 6, we win $1. So overall, how do we fare? It's +1 here, but -1 here. So together, 0. Yeah. Does that make sense, Daviana? It looks like you're struggling a bit with that. Okay. We know that if we choose a 1, 2, 3, or 4, okay, we're -1. But we already paid $1 to play the game in the first place, to even draw a number. So we're -1 here, and then we're minus another one, so we're actually down 2. Okay. For the 5 or 6, we paid $1 up front, we picked a number, and it came out to be either the 5 or the 6. Now that wins us $1, but really what we're doing is we paid the $1 up front, and we win $1, we just got our $1 back. So we're no change to the money that we have in our pocket at that point. We paid $1 and we got it back. So in the 7, 8, 9 case, we paid $1 to play, and then we won $2. So what change to the money in our pocket does that amount to? +1. So we got an extra $1, yeah. Finally, we've won something. And that's how you know it's probably not a fair game, is that very few of the outcomes result in a positive outcome. So, and if we happen to choose the 10, we'll be given $3, but that includes the $1 that we paid up front. So overall, what is our change to the money that we have? The plus and the minus is not necessary. Well, the minus would be necessary. The plus is not necessary. I just like to use it to show that in which direction it's going, up or down, basically, positive or negative. Plus 2, right? Alright. Now for P of x, this is the probability that one of these 4 outcomes occurs. What is the probability that we would choose a 1, 2, 3, or 4 from this hat that has the numbers 1 through 10 in it? Four out of 10. Good. That's 4 of the 10 outcomes right there. But again, we'll make sure we write it as a decimal. What if we draw a 5 or a 6? Point 2. 7, 8, and 9, that would be 0.3. And the 10, that would be a 0.1 probability. Okay. And now we multiply x times p of x for each row and put the answer in the last column. So for the first row, negative 2 times 0.4 is negative 0.8. 0 times 0.2 is 0. 1 times 0.3 is 0.3. And 2 times 0.1 is 0.2. So that's just multiplying across. Then we add up the last column. Negative 0.8 plus 0.3 plus 0.2. So definitely comes out to be negative. And that will be negative 0.3. Now, that was part A. Part B, and I actually separated these into 2 different questions on the exam, just so the grading would work out the way I wanted it to. Part B is what is the expected value? Is it a fair game? Now this is the only problem on the test that's basically you'll just have a text box you can type your answer in. So make sure you answer both parts of the question. So first of all, what is our expected value? Well, the expected value is the number that we just calculated right here. Okay, so our expected value is that we lose $0.3, which is the same as 30 cents if you want to look at it that way. So we expect to lose 30 cents on average. Is it a fair game? No, it's not. The only way it's a fair game is if the expected value comes out to be 0. So if we had gotten a 0 here, then yes, it's a fair game. Anything else, though, not a fair game. And that's all you'll have to type in there. It doesn't have to be real elaborate. I would prefer complete sentences, even though I'm not setting a great example right now. But yes, that's all we really need there. Okay. My hands are getting cold. Can't really wear gloves and write well. My handwriting's already struggling at best. So, yeah. Problem 6. Yes, I could. Where did I put it? It's underneath. The issue with net winnings is that we always have to take into account the cost to play the game in the first place. So when they tell us that we'll win $3 if we draw the 10, it doesn't mean we're going to have $3 more than we started with. Because what happens is we paid them $1 to pick a number, and then we picked the 10, which gave us $3 back. So that means we're down 1, and then we're up 3, so minus 1 plus 3 gives us a net change of plus 2. If we choose a 7, 8, or 9, like we picked out the 7 for instance, we paid $1 to pick the number in the first place, and then we won $2 by picking the 7. So we paid 1, then we got 2 back, so now we have $1 more than we started with, so we're up 1. For the 5 and the 6, we know we paid $1 to pick a number, but then we picked a 6, which won us $1. So we paid $1, got $1. So now there's no change to what we had from before we even played the game. We played the game, and we saw the same money we started after as we did before. And then if we picked a 3, for instance, we know that we had to pay $1. We already paid $1 to pick the number in the first place. So we paid $1, picked a number, and it turned out we had to pay another $1. So now we've paid $2, so we've lost $2. Think of the plus and minus as loss and gain. So we've lost $2 here, we won $1 here, or gained $1 here, and we gained $2 here. It's kind of a combination of what we pay up front and then what we receive from the game. Combine those together. Does that make sense? Okay, good. Let us continue with number 6. Number 6 has been reported that 63% of adults aged 65 and older got their flu shots last year. In a random sample of 300 adults over 65, find the mean and the standard deviation of the number who got their flu shots in this binomial experiment. I got my flu shot on Friday last week. It doesn't hurt anymore. It only hurt for a little while after I got the shot. More of a soreness than a pain. Anyway. So we know 63% got flu shots last year, and we have 300 adults in the sample. And they want us to find the following. Okay. Now, N is either the number of trials, if we have some process being repeated, or our sample size. Sample size and trials are counted the same way. In this case, we know that we have 300 adults, so that's our sample size. N equals 300. P, remember, as P is defined as the probability of success. And in this case, 63% of adults 65 or older got flu shots last year. So our probability of success is 0.63. Now, Q is not strictly given to us, but we know for a fact, and this is a formula that's provided on the formula sheet part of the test, which is like it's the instructions and formula sheet, calculator instructions, and then the actual test is a kind of hierarchy there. Anyway, Q equals 1 minus P. This is our probability of failure. But we already know our probability of success is 0.63. So our probability of failure is 0.37, the other 37% of the time. Okay, for the mean, the formula for the mean is on the formula sheet. It's N times P. So just multiply 300 times 0.63. And that comes out to be 189. And our standard deviation, the formula there is N times P times Q. And then we take the square root of the product. So it's going to be the square root of 300 times 0.63 times 0.37. Let's see. What do we get here? Square root of 300 times 0.63 times 0.37. So it gives us 8.362. Oh, thank you. Okay. Hopefully this problem is pretty straightforward. Essentially, the first two values are already given to us, N and P. Then we can use P to find Q, N times P to get mean, and square root of N times P times Q to get the standard deviation. Those are just fill in the blank. Okay, so that leaves number 7. Probably will need another page. All right. 7. A recent study found that 50% of teenage consumers receive their spending money from part-time jobs. 20 teenagers are selected at random. Okay, so 20 teenagers are selected at random. That means N is 20. And 50% of them have full or part-time jobs. Or no, part-time jobs, not full. And that probability is 50% or 0.50. So this is binomial also, and it's the setup is similar to number 6. The information is given to us in the context of a study or something like that. So N equals 20 and P equals 0.50. We just have to pick out those numbers from that description. But where it changes is in the question that follows. The probability that 12 will have part-time jobs. Exactly 12 will have a part-time job. Now this is actually what we looked at last Wednesday. It's been about 5 days, but anyway. On our calculators, let me start with this one. $12 is our value for x. Okay? So x we defined as the number of successes. So we go into the calculator and we hit second and stat distributions, so second data. We arrow right once to get to distributions, and then we arrow down until we get to Binomial Pdf. Now, for x equals 12, like we have here, we use the Binomial Pdf function. Okay. So we press enter. Now, we always hit single right here. We don't want to have to enter the values ourselves. We'll just give them the data that we already have. So 20 trials. Probability of success is 0.5. And if you enter 0.5, it'll change it to 0.5. And the number of successes is 12. And so we'll calculate. And so it gives us a value right here. And we want to round to 3 decimal places. So put 0.120. Okay. Now, B is actually the one that I'm replacing. Oh no, B is not the one I'm replacing. C is the one I'm replacing. My bad. B, find the probability that at most 6 will have a part-time job. Okay. Now when we say at most 6, first of all we have to make sure we interpret that correctly. At most 6 would be anything from 0 up to 6. So less than or equal to 6. Okay? And we'll use x equals 6 when we do the calculation inside the calculator. And binomial CDF. So when we say at most 6, it means 0 to 6. Whatever this last number is, 0 to whatever, that number is what we use for x. And because we have a range of values rather than a single value like we had here, single value uses binomial PDF. A range of values uses binomial CDF. That way we can get the correct value here. Okay. So in our calculator, let's second data, distribution, and arrow down to option 5, which is binomial CDF. It's single. We have 20 trials. Probability of success is still 0.5, but now we're looking at 6 as the maximum number of successes. Arrow down to calc. You can see we got 0.0576, so that'll round it to 0.058. Okay. Now part C, that's the one I'm replacing. So let's change the question to something like this. What is the expected number of teenagers that have a part-time job? Now, expected number basically means we want to find the mean. Okay? And mean is simply n times p. So take n, 20, times p, 0.50, multiply those together, and on average we would expect 10 of the 20 to have part-time jobs. Okay. So basically I took a more difficult problem, which was the original 7C, and made it easier with this version. Also, this better reflects what's on the final exam, so we should do that. Does that make sense? Or is that okay with part C there? No, actually this test you won't have to upload anything. It's going to be fill in the blank and then one problem where you have to type in a response. So a lot easier in that regard. Yeah, there's no graphing this time, so I don't have to see the graphs. I can just let you enter your numbers, and that's fine. So that should be easier for everyone else, for all of you to complete the test. You don't have to go through those extra hoops. So I went ahead and left the time limit at 120 minutes because I don't want to change it on you all of a sudden. But yeah, that'll be it. Alright, so that wraps up the review. Are there any other questions? I only showed the 36 here today, but if you want to look at how we did it on the other calculator, the 83, that's in our video for last Wednesday, and the instructions will also be included on the exam. And I set it up, I think it's set up to become available today at 2 o'clock, so it should already be available, and it'll run through Sunday night. So we'll have from whenever until Sunday night. We won't have class on Wednesday. Keep that in mind. There won't be a lecture. So if you just wanted to do it during class time on Wednesday, that'd be perfect. But you also have the freedom to choose any time in between by Sunday midnight or 11:59 p.m. So. All right. Well, you all take care. Stay warm. Good luck on this exam, and we will meet again next Monday. So I'll see you then. Bye.